There are also all of these informal aspects of a conference where, like, we had a gathering of all of the women at the conference last night, and it was really nice, and I made some new friends. So that's the kind of stuff that you would miss if you weren't in person.
Thanks everyone for coming out. Really, thanks. I saw the other talks at this time slot. I almost didn't come. I wrote this talk with two main kinds of audience in mind. The first is going to be people who are writing tests for functions that have complicated inputs. So it's a pretty hard problem in general. We're going to deep dive on one concrete example and try to find something from that we can generalize if possible. The other audience is people who have that exact problem. This would be motion planning in an autonomy stack for self-driving, maybe aerial applications, I don't know. If you're in that audience, lucky you. We're going to take some clear, specific paths through design space where we look at the things we've seen that work in practice. So a little bit about the application. I work for a company called Aurora. We're on a mission to deliver the benefits of self-driving safely, quickly, and broadly. We're actually launching our first product this year, 2024, self-driving trucks, long-haul cargo, driver out, Dallas to Houston. So it's a very exciting time for the company. As for me, I'm Chip Hogg. I've been at Aurora almost 4 years. I'm on the motion planning team, and I've been in the self-driving industry almost 9, believe it or not. So I mainly focus on making good tests easy, but I've been wearing a lot of other hats as well. Disclaimer about the talk. The APIs here are not exactly what you would see if you went and got hired in at Aurora, which I recommend. But this is not what that is. It's not onboarding for Aurora. This is instead, the goal is whatever communicates the ideas that we learned with the greatest clarity. So that's what we're going to see today. So let's talk a little bit about tests generally. They come on a spectrum. They range from end-to-end tests. The scope is the whole system. Then you have integration tests, test the parts work together. Unit tests to test individual components. Even compiler errors can be a kind of test at the line or subline level. When you get up near the top, you have bigger scope. There's more that you can test, but they tend to be slower and more expensive, so you kind of have to be judicious with these. Down at the bottom, they are fine-grained, they're fast, they're cheap, easy to understand and iterate on, tight cycles. Now, do we know what the best kind here is, the most important kind? Actually, it's all of them. It's a trick question. I'll try not to do any more of those. They are complementary. They give us a defense in depth, which is very important for what we're trying to do here. So today's talk kind of lives in the middle here. These are like integration tests down to maybe big-ish unit tests. Basically, think of it as things that you would write a kind of classic C++ test case for. So for these things, you've got a test case. Kind of comes in 3 stages. So a range is going to set up the inputs to your function. Then act, you're going to call your function. And then you have assert. At the end, where you test to see whether the thing you got was something that is good or not. Today's problem mostly lives in the arrange portion part, maybe a little bit in act as well. So we know that real-world functions can have complicated inputs, and that's a big challenge. So for example, we have a function here that takes a historical motion as an input and some dt in the future, and we want to predict a future motion. Those inputs can be really complicated. Maybe we have an actor that is simultaneously changing lanes and accelerating. And how do you write that input for a unit test? It's just really hard. And we kind of have 2 bad choices, honestly. We can give realistic data that we set up very meticulously, but then it becomes kind of hard to understand. You lose the intent. It becomes very fragile, maybe, as the code evolves. So alternatively, we could try to make some simple fake data to pass, just something that fulfills the contract, but the tests that we get from that tend not to be all that meaningful. So how do we find our way out of a dilemma like this? Well, according to Tolstoy, all simple function inputs are alike. Each complicated input is complicated in its own way. Fred Fred Tolstoy, my old manager back at Google. Anyway, that means there's not likely to be a sort of generalized theory. Here, what we're going to do instead is pick one complicated input, deep dive, and try to generalize. So the example is going to be motion planning component in a self-driving car. If you don't know how to make a self-driving car, that's no problem. We're going to learn just enough so that anyone can follow along. So start with this black box picture. We know we have some sensors on the input, a camera, LiDAR, GPS, whatever, some black box autonomy stack, and then on the other side, the pedals and steering are actuated. If we refine this picture, we have well-defined components that communicate by passing messages. So sensors tell us where we are, localization, what's out there, perception. We know what part of the map to fetch, how to make a route to get to the goal. And then all these things go into the motion planning component. And its job is to assess the situation and come up with a trajectory, a space-time trajectory to drive over the next couple seconds. So the next component is controls, which knows how to read that trajectory for the specific platform we're on and translate that into actuation. And then, of course, we're going to get new sensor data a fraction of a second later, and we're going to repeat and replan. So that's the big picture of an autonomy stack. Now, how do we implement the motion planner component that we're focusing on today? One common way is by a kind of three-stage architecture. It's pretty flexible. The first thing we do with all these inputs we get is to assess the situation. So we assemble them into a coherent whole. And then we come up with like a bunch of ideas, hundreds, thousands. And then last, we evaluate all those ideas and we pick the best one. So this is a nice, elegant, robust, flexible architecture. So for example, in that middle stage, where you're coming up with a bunch of ideas, you can reserve some of the capacity for a handful of emergency maneuvers that you just always want to consider. And then we will do those maneuvers exactly when they are better than anything else we could come up with. So it's easy to understand, very nice. So assess the situation, come up with a bunch of ideas, pick the best one. Not just enough to build a self-driving truck and get it from A to B. It's kind of a recipe for winning at life, honestly. So going from these inputs all the way out to the output trajectory constitutes one planning cycle. So this cycle is going to be the sort of unit of test for what we're focusing on today. Now we could be testing the whole thing. We could be testing any of these individual main components. We could be testing their subcomponents. Anything like that is fair game. We notice if we had these sort of first inputs, it would be easy to make any downstream complicated inputs by just running the parts of the planner on these. So we've kind of reduced our problem to building these inputs, which is kind of great, but kind of not, because these inputs themselves are really complicated. So the way out here is based on this all-time classic Kent Beck tweet. When you're trying to make a change, first, make the change easy. Warning, this may be hard, but then make the easy change. Now, for those of you who have yet to cultivate this habit in your day-to-day job, it's like a cheat code. It's so satisfying. It's a way to move fast with confidence, so highly recommend. But then how do you go about doing this make the change easy? Well, the absolute first step is you need to figure out what easy would even look like. So if you can't do this, there's no point in going further. But the good news is that this step is really fun. You can imagine whatever source code you would write in your ideal world where you have everything. No constraints here, just brainstorming, no bad ideas. But then after you do that, you put on your judging hat. You step back and you look at what you wrote, and you think, is this feasible? Can you imagine how someone would implement these APIs? Would it be easy to use correctly, hard to use incorrectly? And don't forget to think about the scope. So get clear in your mind about what use cases are the kind of core use cases that you're just going to nail. What are the kind of peripheral use cases, the stretch ones that you can imagine how you would implement, maybe a bit of a stretch. And don't forget to identify the use cases that are just simply out of scope. Remember, you can always build another library to handle those later. So what's an example for motion planning? Let's say we have this 2-lane highway. We're doing 65 in the right lane. We got a car in front doing just 50, nobody else around. We want to run the planner and test that it proposes a lane change to overtake the car. Okay. Well, we got to get a map from somewhere. This API, I don't know, maybe we'll come back to it later. But then we're going to get a lane from that map. That's going to be the lane we're in. Then we're going to build the scene. So what are the things we need to give it? We need to give it the map, the goal. If we don't have a goal, we're not motivated to move. And then we're going to specify the path and along path motion that we are following. Now it's time to add the slow car. So we're going to sketch a car that's in that same path, but 40 meters ahead. Set it to 50 miles per hour, and then set it with the add actor. The timer was really freaking out, but okay. Then we're going to finish this off and expect, that a lane changes lane to what the implementation of that is. We worried about that later. So this source code is pretty readable. Okay, it's easy to picture the scenario. We're mentioning the things we care about, not mentioning the things we don't, because we have reasonable defaults. Even so, I think that it would be nice if we could verify that we set it up correctly by having, as a stretch goal, a kind of interactive 3D visualization. And as a further stretch goal, it would be nice to have a pony. Now, the pony is deferred to the next version, but we can imagine getting this readable this interactive 3D visualization of the scene that we just described here. So that's pretty exciting. Now, let's see how we would build something like this. It turns out that it's built in terms of layers or levels. So level 3 is the scene builder that we just saw, but we can't really have that unless we get level 2, which is a map abstraction where we can get these well-named paths. Level 1 is a foundational set of paths, poses, and motions that are going to build our map and scene out of. And it turns out, actually, there's kind of a level 0 here that's more fundamental than all of these. I wonder if anyone can maybe guess what it is? Units. Got the sticker and everything. That's right. It is a units library. A good units library is critical for this. In fact, this project I'm presenting today is like the reason that this open source units library was created in the first place. I thought about the APIs, what they'd be like without it. I was not willing to live in that world. When we wrote it, we brought in stakeholders from across the world, and this diversity of use cases created a crucible in which it was forged, and it became all the stronger for it. So we went to CppCon in 2021 and talked about what we learned, the properties that a good units library should have. The one slight problem was that at the time, no public library actually had all these properties. You had to go get hired in at Aurora, which I recommend, but still. I felt a little bad about that, so we open sourced the library and then came to CppCon 2023 and presented it there. And I'm almost done saving up enough money for another shirt. So that's level 0. Level 1 is the first kind of true foundational level. These poses, paths, and motion. We're going to build everything else on top of these. So pose here, if you're not acquainted, pose means where. It's a position along with an orientation in space. The job of this type is, given some starting pose from somewhere, it needs to be easy and readable to make a related pose. The strategy for that is going to be some chainable APIs, so we can chain some transforms. So for example, we can take a starting pose, we can move it forward by some distance, we can turn, and that's going to default to 90 degrees, but you can put an angle in there if you want. We can even execute more complicated motions, like constant body frame curvature, forward motion. So this foundation is going to make it really easy for us to get related poses from some starting pose, but where does that starting pose come from in the first place? The opinionated, strong preference that the library has is we should always be getting that pose from meaningful physical paths in the scene. So X, Y, Z, theta, that's right out. We really want to avoid that if possible. That's going to be fragile. It's going to be hard to read. Users are constructing a grid in their head, not what we want to be doing. So here's a path. It's the right boundary of the right lane of the road. If you give it in a long path position, that's going to give you the pose. And then you can move it to where you want. So you can move it to the right, turn it left. That's a readable way to say, this is a pose that's facing the boundary from this distance. So that's a pretty good start. There's kind of a problem coming up here with these paths. We have a right boundary of a lane. The next thing we're going to want is the left boundary of that same lane. It would also be nice if we could kind of line them up with the position markers, and here we see the problem. The positions are going to get out of alignment. The inside track is just more efficient for travel, we know this. Now we can force align them, kind of shoehorn them in, but then the position differences on that inside track are not going to be accurate. They're going to give the wrong distance. So what do you think here? First approach, second approach, any strong opinions? Who thinks first approach? Okay. Hands for second approach? No? Okay, good news. The real world has this problem too. So we can just steal their solution. It's great. That would be mile markers. Got to go pick up my son. Not today. That'll be mile markers. The positions aren't exact measurements. They're just kind of labels for points. So when you get a position difference, it's not guaranteed to be an exact physical displacement, but it should be pretty close. Like if you drive from the 3 mile marker to the 5 mile marker, you probably went about 2 miles. So these are a little bit looser, but that makes it a lot easier to write the tests. This is kind of similar conceptually to, in the chrono library, we have time point as opposed to duration, and it has kind of the same operations. Like the time point, you can't add 2 time points. It doesn't really make sense. Can't add 2 mile markers. But if you subtract them, you get a displacement or a duration in the chrono case. So mile marker math. So now that we've seen this kind of core problem, we've seen how to resolve it, we're in a position where we can appreciate the path type that we made, which we call ribbon. Mathematically, a ribbon is a 3D path through space that has a bit of surface orientation attached at each point. And if you kind of squint, that's kind of equivalent to specifying a pose at each point if you assume that the pose points along the path. So that's ribbon. We say that ribbon is road optimized. What we mean by that is that its job is to translate between position differences and physical displacements. So let's take a point P. It's going to be at the 10 meter position. What the ribbon can do is if you advance that point by 10 meters, it can tell you what position you're at. In this case, it's the 21.8 meter position, not 20. It can also do the reverse. So if you go from the 10 to 20 meters and you say measure that distance with this function here, it'll tell you it's 8.5 meters as it happens in this case, not the full 10. So paths like these can act as basic reference frames for the scene. So for example, if you're placing an actor in the scene, it's pretty natural to specify as you pick a path from the scene and you specify the along path position where that actor is currently found. And in fact, this pairing is so useful that it deserves its own type. That would be relative path. So remember, for ribbon, we give it an along path position, a label of a point, and then we get the pose. For relative path, we give it the distance from some starting place, and it is a physical displacement. We'll see why when we look at composability in a little bit. Now, relative path is designed to be an interface type. It's a thing that you should put in your APIs that they should accept, and we'll see why now. It gives you some nice call sites for calling APIs such as this example one here. So set actor path, we're going to give it a relative path. What are some ways we might do that? One way would be to pass a braced pair of the path and the along path position. Now, if we look at the call site, that's pretty readable. We can understand what is meant pretty naturally by that. Another very common use case is to just simply pass a single pose. And if we do that, it will automatically generate a relative path that is a straight line going through that pose. So that's this constructor here and this call site. This is really useful because we're often going to want to construct a test that has, I don't know, a pedestrian facing the road, right? And that path, that implicit path that they would be on, is not going to correspond to any pre-existing physical path in the scene. But we've seen how easy it is to take a starting pose and transform it. And so we can use that and then just take that transform pose, pass that in, very natural. So that's pretty useful. So now that we have the path abstractions, we can talk about the along path speed profile of the motion along that path. We have this type, which is creatively called motion. And it basically, the job here is to map the elapsed time onto the elapsed spatial distance, along path distance, and all time derivatives. So you get the displacement, the velocity, the acceleration. We could add more if we want, so on and so forth. It's returning motion snapshot, and what that is just kind of what you would think. It's a struct that has the displacement, velocity, acceleration. Okay, and motion itself has a very interesting constructor here. It is implicitly constructible from any speed type that you get from the units library. Motion, like relative path, is designed to be an interface type. It makes your, if you take it in your APIs, it makes them more flexible. Let's see how. If you have an API that is, you're kind of tempted to take a speed, like it would be a constant speed API. If you take motion instead, users can still pass that same speed at the call site. So you haven't taken anything away. But you can also pass more complicated speed profiles in that same API. And every time somebody makes a new one, your API gets more powerful, more expressive, without changing a line of code, which is great. There's going to be other polymorphic constructors I kind of glossed over here to make that possible. There's a very natural composition between the relative path and the motion. Given a dt compared to time equals 0, that dt will give you the long path displacement ds and the velocity and acceleration. And then that ds, in turn, you can feed that into the relative path and get the pose. And also the curvature, which I kind of glossed over. I left out of the slideware, but we do have that as well. So you kind of get all the vector quantities, spatial derivatives, time derivatives. It's all there. So that's really nice, because it means that when you build an API, when you build a scene in terms of these types, it's not just a static snapshot. You can query the whole scene at near past and near future times. And the motions that you get out of this are going to be kinematically self-consistent. So if you take a given dt, a given snapshot, you get a pose and a velocity, then the pose that you would get a short time later is to first order what you would expect from that velocity. So that's just, you get all this self-consistency automatically with these interfaces. And here's what that would look like in code. Just expressing that idea in C++. As a kind of aside here, the way that we write these types, we use polymorphism, of course, but it's kind of hidden from the end users. So here's, for the ribbon, here's a ribbon implementation that any ribbon implementation would have to satisfy or inherit from, but the end users are not going to see that inheritance directly. Instead, we have the ribbon type just take a shared pointer to const of some implementation of that. Now this is very important. If it was a shared pointer to non-const, it's basically a latent global variable, which doesn't get me out of bed in the morning. But shared pointer to const actually gives this type value semantics. There was I think a Sean Parent talk where I learned this enchanting idea. And it gives your type the size of shared pointer, no matter how complex your implementation is. So these turn out to be little lightweight, immutable types. You can pass them all around your program. It kind of doesn't matter how you do it that much, by value, by const ref, whatever. They're just very easy for end users to use. And the way that you would implement the API functions is kind of obvious. You just delegate to the shared pointer. We've seen a lot of talks about reflection here. Doesn't this feel like a nice application of reflection generation? Yeah, I'm definitely hoping to live in that future. So that's level 1, poses, paths, and motions. Level 2, map abstractions, is the next thing we build on top. This is going to be the place where you get your meaningful, well-named, physically meaningful paths. So it turns out, in our experience, there's 2 kinds of local optima in design space that can work really well here. One is what we call the map sketch. This is where you have a fully synthetic map, or kind of a high-level description of a map. And the other is what we've been calling backdrops. So this is where you have a pre-existing map data structure, full complicated map data structure. And to make it more user-friendly, you just you create these path objects and then you bundle them together. So these are the 2 that we've seen work really well. So for example, this would be the right boundary of the right lane in this real-ish map. We'll start with a map sketch, go into that a little bit. The way that you make a map sketch or a road sketch is with a road sketcher. So these are going to be readable synthetic roads. Here's kind of the simplest API. road sketcher.finish lane and road. Okay, well, that's going to give you a 1-lane road. You can call finish lane and start another, and we see that the number of lanes you get is the number of times in your code you say finish lane. So this is easy to learn how to read. We can also take any ribbon and make that the road frame, and then the road is just going to follow that ribbon that we gave it. If we want a shoulder, we can set the shoulder width on the left or right side. We can even turn off the lane change availability between 2 lanes, or if not to turn it off completely, we can have it start at some point in the future. In fact, we can even take this lane and kind of break it off here, say convert to on-ramp at 50-meter position. So there's a lot we can do. There's a lot of roads that we can concisely describe and then synthetically create a high-level description of. So that's how you make it with the sketcher. The way that you use it is, well, it kind of depends on the role that you're playing at any given time. And there's 2 main roles here. The first role, it's kind of obvious. It's the one we're mainly talking about. It's you're writing a test case and you need to make a road. So in this case, the road sketch is going to be acting essentially as a bag of well-named paths. This is what we were talking about earlier. This is not a surprise. So that's that. You also are going to need real map data structures as the complicated inputs, some of the complicated inputs to pass to your functions. And remember that the map sketch or the road sketch is not a map. It is a high-level description of a map, so it's not a thing you could pass to your functions. So what's the dependency relationship here between these 2 things? Like, I don't think we really want the map sketch to know about the concrete structures, because there may be many different ones for different functions. And we definitely don't want the online onboard data structures to know about our test-only map sketch. So it turns out that the dependency direction is none of the above. It's neither. The strategy here is to write a builder class that depends on both. And so the builder library is the kind of other role here. So it's going to take a map sketch, doesn't know the details of that sketch, and use this second set of APIs to kind of iterate over that data contained in that map sketch. And then its job is to construct whatever kind of map data this function is using in a way such that it is consistent with the high-level description in the map sketch. These APIs here, they're pretty different. I like to think of them affectionately as clunky yet precise. They are talking about, like, you iterate over the lanes, you iterate over the regions within the lanes, but this is the second set of APIs. You might have picked up, it's kind of, like, it's cool that we can do this, but it also feels like a lot of work. You're not wrong. And sometimes, just to build that map, sometimes we just already have a map that's accessible in our unit test. So you might have a chunk of a real map that is already made available to the infrastructure where you're running your tests. It'd be kind of nice if we could just use that. And that's going to be that second option where we take that and just supply it what it is lacking, which is these well-named, physically meaningful paths in the scene. So this is what we've been calling backdrops. A backdrop is not a scene, it's the backdrop against which a scene takes place. What is it, actually? Well, it's just a class that has kind of the kinds of members that you might expect. We've got a member to hold the actual map data. We've got all these lane members that hold the sort of buckets of well-named paths. We have some physically meaningful positions that make sense for this specific scene, that kind of thing. And then to access those, this is just kind of an aesthetic choice. We're using hidden friend functions so that you would say the left lane of the road instead of road.left lane. It's just a small aesthetic choice. You know, we can disagree about that. In order to construct it, you have to go look at the actual map data, which is meant for AVs. It is not meant for humans. It's going to be a bunch of segments that are like indexed by GUIDs, and you have to kind of figure out which ones correspond to the well-named paths you're trying to build. And then you get to write fun constructors that put all the GUIDs in the right places, and you're going to want lots of unit tests for this specifically. But you can, this is doable. It's tedious, but there's very little technical risk. And then, of course, just to reemphasize, this subsequent lanes after the first are going to have a second argument to say which previously made lane data structure are you going to align that position frame to, because we want the positions to really act like mile markers. So yeah, it is labor intensive, but it does make it really easy to get that full map and nice pass. So to compare our options here, if you get either one of these in a test, they're really easy to use. They're just a bag of well-named paths. Making one for the sketch option is like super easy, super readable. Backdrops is a pain. There's just no way around that. It's a lot of work to make each backdrop, and then you hope you would reuse it for a great many tests. Now for fidelity, the sketch approach it can be good. It can be as good as you make it. It can be as much effort as you put in, but it does need a big investment. Whereas like the backdrop, you started with like complete map data already. And then the startup cost, if you already have these chunks of atlas for the backdrop, or chunks of map for the backdrop, it's very low technical risk to build this on top. There's a lot more work you need to put in to get the sketches off the ground. So now we have user-friendly poses, paths, and motions, that's level 1. Some solution for map data that gives us meaningful paths, that's level 2. It's time for level 3. Let's write some actual tests, okay? We have reached that stage. And for motion planning test cases, these are typically phrased in terms of a situation, in terms of a scene. So level 3 is going to be the scene builder. We're going to start with this kind of very basic example. We'll walk through the code here. Let's say we're using the backdrop approach. We have a highway merge with a subsequent exit coming up. Okay, you can kind of picture that. We're 65 meters behind the start of the merge where the lanes come together. Now, when describing the scene, it turns out there's kind of 2 categories of input, 2 categories of data to give it. There's the data that it just always needs to have. And then there's the data that's more optional. Like not every scene is going to have other actors in it, but it's always going to have a map. So we're going to use the constructor for the things that need to be there every time. And that's kind of a way to communicate to the user the requiredness of these. So we're going to use a technique that I saw on one of the posters. Obviously, we had it in the code before that. So we're going to give it these with designated initializers and an unnamed struct for the argument. So we have the map. We have a goal, because if we don't have a goal, we're not motivated to move. Final pose of the right lane of the road. This is readable. And we have the path and motion of the eagle vehicle, us. So this is the things that we described earlier. Then we run the full cycle, and we're going to expect that we get a valid plan out at the end. Not very strenuous test, but you got to start somewhere. So let's see, can we picture this scene based on this code? We have some kind of a highway. There's going to be a merge up ahead and then an exit after the merge. We're in the right lane. The merge is going to be 65 meters ahead. Let's see what we get. So we can see from the distance rings, there's kind of 65 meters is about here, which looks like where the merge was. So that's pretty encouraging. And then if we kind of get rid of the rings, zoom around here, we already saw that the merge was there, and as we zoom in and look, yeah, we can kind of see that exit up ahead. So yeah, we have a readable test. We can verify what we thought we were making with these interactive visualizations. So that's very encouraging. All right. Now let's do something more complicated. We've got the core scene. Let's start putting actors in that scene. The way we're going to do that, as was hinted on earlier slides, is via an actor sketch, just like the map sketch. It's just a high-level description of the actors. So you can query properties of one of these actor sketches. What's the ground pose? What's the length, width, height, that kind of thing. And then it's just going to store some data under the hood. So that data is going to include some kind of ID so we can track them consistently over time. The path and motion, you probably expected that one to come. Maybe an actor category, like is it a vehicle or a pedestrian or something. And then the extents, a kind of bounding box to tell you how big this actor that we're dealing with is. So let's see. And of course, the next thing we can do is we can take this actor sketch and we can convert it to that full-fledged actor that the production system actually expects. And I want to emphasize here, when we do this conversion, because it's based on ribbon and motion and all that, we automatically can generate a kinematically consistent history of past observations of this same actor. So we automatically get this really high fidelity just from using these types that we've made. The way that we make the actor is with an actor sketcher. I'm not as creative as I'd like to think. So it's going to take the kinds of things that you might expect. We got a relative path, just like before. You can set the motion, you can set the category, length, width, height, all that kind of stuff. This is okay. It's a little bit verbose. This is not what we want to use in end user code. We have pre-configured sketchers, basically a sketcher returned by a function. This one's called car sketcher. And we automatically set the category to vehicle. We set the extents to be roughly car sized. So when you see this kind of in your unit test source code, it's going to make it more readable. Intent, intent, intent. Channeling Steve Ballmer. So we also have like a truck sketcher, pedestrian sketcher, all this kind of thing. Just little things you can do to make the source code more readable. Okay. Now let's go ahead and add those actors to our scene. This is the snippet that we had before. And we want to add some actors using these APIs that we just saw. So let's add a car at the on-ramp in our same position, our same lateral position. So we got a kind of a spicy merge coming up here, same mile marker. They're going to be doing 65. We're doing 65. We'll see how it goes. But actually, we could use a more realistic scenario. If they're on the on-ramp, and they're doing 65. They probably weren't a second ago. They're probably getting up to speed from some other speed, and they're probably going to the road speed limit, which might be 75, okay? So instead of set motion 65, we can say accelerating from 35 to 75 at 2 meters per second squared, currently 65, okay? Now, if we look at this API, this Fluent Builder API that spits out a motion at the end, could we imagine how to implement something like this? I think, yeah. I mean, I did, so I'm biased, don't listen to me, but like I think we can understand how to do this, right? And this just shows, again, why do we take motion in our APIs instead of the speed? You lose nothing, you gain everything that the future has to offer you. Okay, so we got a car. Now we're gonna add a pedestrian that's facing the on-ramp 3 meters away, stopped. This is nothing really new. We've seen all these before. So can you picture this scene that we've described in code? I feel like I can, but we always have to have those visualizations. So here we go. Oh, no, here we go. There they are. So I do apologize that they're kind of just showing the current position. We're not really seeing the velocity, the direction that, but based on the code we wrote, you can probably intuit that that is also correct, I promise. So we've seen a lot of these visualizations, by the way. Some of you are a little curious where those actually came from. You didn't really see it in the code. Okay, I'm gonna come clean. Here's how we do that. So here's an example scene that we have here. We're gonna run this cycle through Ranker, and it's this run cycle through that is gonna show the way forward. So we have this other struct here, which, visualize test. It has a string, fail and visualize to. So we're going to use that same kind of call site trick before, where we just pass a nameless struct. We say .fail and visualize to my test. So if this is not empty, what this is going to do is take the data that describes the scene, send it up to an S3 bucket where Aurora's standard web tools know how to read it and know how to make a 3D visualization. So that's really easy for end users to do. Why fail and visualize to? Well, a couple of reasons. When the test fails, it can spit out some output like, the URL to go visit. And also, you probably don't want to land a test to master where it's trying to send data to S3 every time you run it in CI. So that's kind of the idea there. All right. So all of these APIs, they're high level, they're intent-based. It feels very satisfying. It's also really kind of great for maintainability as the code evolves. So let's see some examples there. Let's think about construction. We've seen a lot of these orange fellows around Aurora this week, if you've been driving around. How do you describe a construction blockage? Well, physically, it's just a bunch of barrels and a bunch of places, but logically what it is a boundary. And what a boundary is a path, and oh boy, we have paths. So that's pretty exciting. So the strategy here is going to be to describe the boundary. We're going to select a sort of main path from the scene, one of these paths along the road. We're going to add checkpoints at certain along path positions, and we have the ability to add lateral offsets to each checkpoint, which is very important for something like tapering the barrels. Okay, and then to finish it all off, we take those checkpoints, we have a piecewise linear connection, and then when it's time to actually run the planner, we just drop barrels along that boundary that we've described, and if we're blocking the left side, the barrels go on the left, and vice versa for the right. So let's take a look. Here's an example test case, and we want to add some construction. We want to have a blockage boundary. So we're going to make a construction thing equal something, and then we're going to have down here .add blockage as a kind of fluent setter for the construction. Let's build it up. Block left side along right boundary of left lane of road. It is readable, maybe not super fast, but if you look at it, it's like, okay, right boundary, left lane, that's the dashed line. Our main path is the dashed line. Okay, so what is the boundary going to be? Well, we're going to start 50 meters ahead, and we're going to move it left by the width of that lane. Okay, so this is like the start of a taper. So from 50 meters through 100 meters with no offset, so now we've returned to the dashed line, to 250 meters. So when we look at this code here, do we think we can picture where we expect the barrels to pop up in this diagram? And if we could, did it look something like this? Okay, if we curved this road, the barrels would curve with it. It's just really very satisfying. So, and again, the importance of being able to taper with those lateral offsets. Now we talked about this as implications for maintainability, right? We just saw a readable, flexible way to place physical barrels in our scene to describe construction. Now, that's how we describe it from the outside. From the inside, how does the planner reason about construction? And there's a couple different options, many options. Maybe one possible set of APIs to start would be a categorical implementation where we say, at this region, is the lane fully unblocked or fully blocked or partially blocked, where there's barrels encroaching, but we can still fit. Maybe that would be not a bad starter API. We could also imagine a more continuous API where the API is, you give it the position along the path and it will tell you the navigable space. So that might enable us to do more sophisticated reasoning. Now these two implementations, they're very different, okay? So if we want to refactor from one to the other, there's gonna be a lot of code changes all throughout the code base. What won't change is a test that is written in this way. Nothing about the test has said anything about the implementation. It's high level, it's intent-based. We know the kinds of tests that do more harm than good. You want to do a refactor, you end up refactoring all the unit tests. It's just nice to have intent-based APIs instead. Okay, everything we've seen so far is all about what the end users will write. We might also be wondering, how does this actually work? We might also be wondering, does this actually work? And I will tell you that it does, but you're going to have to take my word. So the scene builder, what it is doing is it is building up a data structure that we call scene description. And this is basically a simple struct. It's got the data you would expect for the map, the goal, and so on. Some of these are nested structs, and they have the things you would expect. So like the ego state, got to have that path in motion, we know by now. Probably also a turn signal history that's definitely important for some kinds of situations. And so the implementation of Scene Builder is just going to hold one of these scene description objects and just be building it up over time as we pass more and more data to it. We have these fluent APIs we saw, like .add actor. The implementation for those functions is pretty straightforward. You're going to put that actor on the list of the things you saw, and then return this is how we do the chainable fluent APIs, kind of a standard builder pattern. So nothing here is like super interesting or earth-shattering, but here's the way that it actually helps what we're doing. So remember, we have this sort of pub-sub architecture. The modules are passing messages to each other, so they're generating messages, and then over time the buffers are filling up. And at the time where we start one cycle, the planner is in some state where it has message buffers for each of its inputs, and they contain some set of messages, each of which was generated at some particular timestamp. So we want to make this in a unit test. We have this scene description. We want to create this situation. What is the way that we do that? And this is actually really nice because the problem decomposes beautifully. You can take each planner input independently and ask the question, in this situation, in this scene, what contents would I expect this message buffer to have? So the decomposition is really nice. We can take the ego pose. It's kind of obvious what we're going to reach for here, the ego path and motion. Again, kinematically self-consistent history here. Very nice. To make a map, you just kind of get the map. That one kind of just is what it is. For the actors, we're going to read the list of actors. That's kind of obvious, but we also are going to look at those construction boundaries that we put there because we need to know where to drop the barrels in the scene. So that's how we know what kind of data to create. Next up, we want to look at the data structure that we use to store that data, because we're going to be populating this data structure and then filling all the message queues from that. So in order to understand that, one thing that we do for each of our planner inputs, our input channels or topics, is we have a tag type that represents that input. And you can use that tag type to refer to that input in code. So each tag type will tell you the concrete type of message that is being passed. And we also create, we sort of pre-create these canonical instances of each tag type. So this all caps ego pose is an instance of ego pose tag, etc. A time message for one topic is pretty simple, just a templated struct. You got the timestamp, you got the message. Now, if we wanted to get all, we also have this tuple of all planner inputs here. So this is just a tuple of tag types that gives you a way to reason about the set of all inputs that the planner has. You can imagine if you had this in your code, there's probably a lot you could do with it. So in order to get the all messages for all of the different timestamps and topics, we're going to have this timed messages for each of planner inputs, which is kind of what you would want to see. And of course, this is going to shake out to a tuple of vectors where the vectors are holding timestamp messages. The way that this works, don't worry too much about this. This is a pause it on YouTube slide in case this is just the standard template metaprogramming stuff. But the real takeaway here is that time messages for each of planner inputs is this tuple of vectors. That's what we want to have in mind. What does it look like to actually use this thing in code? Well, we can make this tuple like we have here, and then we can retrieve an individual vector. So it's just std vector of time message of ego post topic and pass the messages. What could be simpler? Well, I'm going to tell you. So what we want to do instead is wrap that in a class called scene messages here. That's going to be the sort of logical equivalent of this tuple of vectors thing here, and it's going to hold that raw implementation as a data member. And then we're going to have a templated square bracket operator that's going to receive instances of the tag type you want to index for. So we saw that call site on the left. If you use this instead, the call site on the right looks like this, just scene messages, and then to get the ones you're interested in, just messages ego pose. It's just a lot friendlier. So this is the thing that we're filling up from the scene description when we're ready to make the test. Before we see how, we need to look at one more use case, very important use case for the work we're doing, which is testing fault conditions. Not everything always goes as you would want. We need to make sure that the planner is going to detect faults appropriately and respond appropriately as well. So we'll start with a kind of basic test, non-fault test, and then we're going to see how we would want to modify it. What source code do you wish you could write, right, in order to test faults? So let's imagine that we are in a situation, we stop getting ego pose messages. That's pretty bad. So what we have is .add input tweak for the ego pose. We're going to set the latest age for the latest message to 1 millisecond beyond the staleness threshold, whatever that is. And then we're going to expect that the result that we get, when it reports its issues, it's going to report that the ego pose was lost. So pretty understandable test case, concise. So let's see how we go ahead and do this. Or alternatively, we could do a different tweak where we invalidate the last message, and then we'd see that we detect a different issue, that the last message was somehow invalid. It violates the contract. So there's two separate questions. We decompose the construction, the filling of the scene messages, into two separate questions for each individual topic. So first of all, In this situation, what times would we expect to get a message on this topic? Secondly, for this topic, what contents would a message have if it arrived at a given time? So separating it out in this way, the key that makes this so useful is that you can take those tweaks, they can apply to that set of times before we even build the messages. And that's really important because that means that the message contents will reflect the tweaked time. So if you're maybe very stale for getting information about the actors in the world, it's going to tell you where those actors would have been at that stale time. Okay, so an input tweak is just a struct. We've got a variant from tuple planner inputs. That's just like a variant of each planner input tag. It basically lets you pick one planner input. And then we have a variant of tweaks here where you can have drop all messages, you can set the latest age, et cetera, et cetera. So some examples here, what that looks like kind of pictorially. If we have some untweaked inputs here, we're going to build the message that's at t minus 200 milliseconds and then build the message that's at t minus 100. We can add a tweak to set the latest age to 600 milliseconds. And the implementation is just going to shift all messages in time, so we get 700 and 600 instead. If we do drop all, we just empty that vector of times, and we never even call the build function. And of course, if we invalidate last, the times stay the same, but then you take that last message and you transform it to be invalid. The point here is that this makes it very easy to write readable tests for fault handling situations. We can make sure the planner raises the right fault. There will be other complementary tests to make sure that if raised, we have the right response. Okay, so wrapping it up, I'm going to have two main conclusions here. There's going to be one for each of the core audiences. On the core problem we dove into, motion planning tests, we remember that the planning problem here is we have a situation, we want to come up with the best plan for that, and our solution was based on a hierarchy of levels. So level 3 is what end users see. It's got the scene builder, nice interfaces. That's based on level 2, the map interfaces, where we get readable, physically meaningful paths that make our tests easy to understand. Those are built on the foundation of these poses, paths, and motions that compose really nicely, make it more than just a static snapshot. And of course, it's all based on the foundation of level 0, which is our open source units library. It's kind of interesting. Actually, as you go down these levels, each one gets more broadly useful. So level 3 is basically like Aurora motion planning only. Those level 1 types, though, like they could be useful for a variety of teams all across Aurora. And then level 0 is going to be helpful for people even far beyond Aurora, including specifically you personally, YouTube viewer. So we have these intent-based APIs that are going to help us as the code evolves. They're going to bend and flow and evolve with it. And we can even handle fault conditions in a readable way. So that's pretty exciting, but that's one concrete problem among many. Is there a general case here? Maybe. We're going to have to see in the real world, but I think this would be the first thing I would try in a different domain. First of all, know your domain. Know it deeply. I had to spend a long time thinking about these problems before I could, for example, understand the mile marker solution for aligning paths. So that's the first step. Second step, figure out what easy would even look like. This is the fun step, the creative step, right? Just imagine you had everything you want. What would you be wanting? What would it look like? And then you put on your judging hat and you try to picture writing the implementation. What will users try to do with this? Is it easy to use correctly? Is it hard to use incorrectly? And don't forget about scope. Don't forget to identify your core use cases, stretch use cases, and what is just out of scope. So I would love to hear about how this actually ends up generalizing in the real world, and I'd love to take any questions at this time.
Hey, great talk. Sorry to say I had a question way from the beginning when you were describing the paths and 0 meters, 100 meters, 200 meters.
Yep. I did the escape on the wrong window. Let's fix that. And yes. All right.
Well, it's kind of the question that I had about it was that when you were saying like, oh, there's the two options, like, here's 100, 200, 300, and here's 100, 200, 300, they don't line up. And then you discussed what the solution was. Was the solution that you were saying that the right one was like the reference, and then this is the projection onto where it would end up?
Yeah, it's basically exactly that. We've got some reference path where like those position labels, they really are accurate, like physical distances. And then we just sort of laterally project from that.
Gotcha. That makes sense.
Yeah.
Thank you.
There's also other APIs that this has that I didn't mention for time, but this is kind of the core idea for this audience.
Hey, thanks for the talk. It was awesome.
Thanks.
I had a question. I understand here we're talking about single motion planner steps, but it seems like you could use something like this in a multi-step process if you wanted to. I'm just curious, like, do you do that? Like, what's the switchover point to full simulation?
That is a great question. The relationship between this and full simulation, there's a lot to say about that. Generally, we don't. We generally stick to the single cycle case here. When we talk about those use cases, core, stretch, and out of scope, multi-cycle is somewhere between stretch and out of scope, depending on how ambitious you're feeling on any given day. But and I think there's a couple other things I want to say to put this in context. One is that the things we are testing are categorically different between a simulation and a single cycle test. So a simulation is going to test behavior of the system. A single cycle test is going to test decisions. So when we think about a defense in-depth approach for testing at all different levels of the system, those are complementary to each other. And the single cycle tests are maybe more useful for developers to get those tight iteration cycles and make it easier to hone in on the root cause. There's other interesting things to talk about, like input space funneling that simulations do. You kind of can't test a case that you wouldn't have driven to in the first place. And single cycle tests can let you kind of expand the input space to the sort of near reachable space in input space. So that's another kind of difference as well. So I hope I've answered the question you asked and the one I wanted to answer as well.
Thank you.
Hey, a bit of a meta question. I don't know how much you can get into it, but
No, I don't work for Meta.
I was curious, how long did it took you to develop a system like this? What was the process for that like? I work for like a smaller company doing like kind of similar stuff, and it feels like this would take like years, and that's obviously, like while you want to keep developing motion planning code as well. So like if there was like a previous system which sucked, how did that transition look like? And
Oh, that's a really good question. Some of this was kind of fortuitous timing because Aurora acquired my previous employer, Uber ATG, and so and the company size kind of tripled overnight with that acquisition. So that could go wrong in so many ways, and it went so right. But like as we were kind of trying to figure out how to get everybody rowing in the same direction, there was some room for kind of experimental shots like this. So it took like on the order of like 6 months to where we could start writing tests. But then once we had it, it kind of took off like wildfire. Like in that first year that we had it, we ended up with more integration tests of this type than we had had in like the previous like 4 years combined. Like this was just so much easier that you get like more tests, and it's really energizing.
Sorry if I can ask a follow-up.
Please.
So the ideas in here were something that you had been thinking about with Uber as well, which you like got into with the context of Aurora when the merger or whatever happened.
Yeah, it had been rolling around in my mind before I even joined Aurora, and then I had the chance to make it real, and then now we've been like using these for like a couple years now, right. 3 years or thereabouts.
Awesome,
so,
thank you.
Yeah.
Wonderful talk, Chip.
Thanks.
And also inspiring, great work, really cool. This looks really like a great setup for scenario-based tests for these scenes that I want maybe to put together. Do you also have something like constrained randomness for your tweaks so that the system can produce more test cases that are constrained in some different way?
Kind of like parameter sweeps, but maybe with like some regions of the parameter space for that test constrained out.
Or like every once in a while a cone is missing, or things of that sort, or it got shifted one way or the other, but the system's able to, within some constraints of reality, produce those tweaks for you?
Yeah, I think it gets to the what we were saying about the use cases and the core, stretch, and out of scope, and then for the out of scope, you could imagine applying some other, or you could imagine making some other library. I think we could apply that idea at the level of the construction helper, although I think that might be a little bit difficult. Yeah, I think I got a little sidetracked from. Screensaver, from your original question, which was about a kind of like constrained random. So to the extent that you're talking about doing some kind of parameter sweep, that's kind of orthogonal to these APIs, and we do that, but not in any. There's no like formal API to support that. It's just kind of C++ code.
Thank you.
Yeah.
Really enjoyed the talk. Thank you for this.
Thanks.
So I feel a bit spoiled because my team, our product is like a model. So we already have a simulation environment, already have a way to create the stuff. It's still difficult to do, still tedious, but the biggest problem that me and my colleagues have is really on the test acceptability side, the test acceptance criteria, and automating that so it's not just a human being looking at a plot and then making some decision inside the CI/CD cycle. What does it look like for you guys? And for instances where you have like a stochastic input, how do you verify so that it's not a flaky test?
That is a good question and a hard question. So I think first, the way that, if I can frame your question, we talked about arrange, act, assert, and I was talking about arrange for 50 minutes, and now you're saying, hey, there's also assert. Is that fair?
Yeah, out of scope of the presentation probably, but if you have any insight,
It's still a fair question. No,
Sure.
totally. The strategy, the main strategy that we use Google tests internally. So we'll try to write like custom Google mock matchers that express these kind of higher level. We saw some of those here, like performs lane change. There should be some function that can analyze the trajectory and a map to see if it's like planning to change lanes. And then you give like a nice well-named API for that. And then that matcher needs its own unit tests, et cetera, et cetera. There's a second part of your question that I can't answer until you remind me what it is.
So if you have stochastic inputs, so for example, let's say your sensor has error, and so you want to run with a lot of random seeds. So, but your test can be flaky if you're just like comparing to an exact time history or whatever historical data, because then anything that changes in your implementation could maybe change that, right? So how do you make it not flaky?
Also, a very good and hard question. We typically try to avoid actual randomness or like different seeds. Like what I think would do in that case generally would be to just try a bunch of random seeds and kind of hope that that's giving us enough coverage. And then if it's something that we're extra worried about, then we would bring in fuzzing to try to like really kind of stress test that API. But we want it to be deterministic but pseudo-random, so that we want the same test to give the same results every time, because otherwise it will be flaky, and we just don't want to do that.
Thank you.
Thank you. All right, thanks everybody for your attention. I know there's a lot of other places you could have been. It means a great deal to me, so thanks.